Greetings, welcome. So in recent videos we've been taking a cap, discharging it one to another by filling a cap up through this circuit and then, through this switch, and then discharging it through this switch and then through a coil of wire. And we demonstrated that if you have a diode in place, this cap doesn't equalize to the same voltages as the cap that you initially started with. So in other words, pretend this is a big cap, 1000 UF, and this one's again 10 UF. And it's 10 volts, so when you discharge it through a coil and a conducting diode, this ends up at like 17 or 18 volts, and your big cap correspondingly goes down a little bit more because charge is conserved. You're just discharging one cap into another, and so there's no place for the charge to go. It follows Ben Franklin's conservation of charge. But it is interesting because you think when you discharge one cap into another they equalize at the same voltage, but you can set it up where they don't have to. And then in a more recent video we showed that the two caps are oscillating like an LC tank circuit. They are an LC tank circuit, just with two caps instead of a cap, just one cap. And so you can use the timing to do the same thing and get rid of the diode. In this video, though, we want to talk about, the limitations with this, as well as how we can get around the limitations. So here we have the test bed set up like we've done in a previous video. We've got this big 10-pound coil, and that's so that you can see the effect a bit more dramatically even with these somewhat larger coils. We have, it's not focusing, but you can see it's a conducting diode. So this discharges the positive here through the conducting diode into the coil of wire to the positive here, and the negative is connected to the negative there. Here's the code for that. I'll attach this to the video description, and we're just gonna let it discharge and then wait 2 seconds to see what it does. And then there's another switch out there that just shorts this out. So what do we see? We see it going up to 16 volts, and we're at a 10 volt input. So that's kind of interesting. You went from 10 to 16 volts. Now what do? You think about it, you're kind of stuck now. How could you get this to go higher than 16 volts? I mean, it was nice going from 10 to 16, and as I said, because everything is just one cap discharging into another, charge is conserved. And there are, well, I can think of 3 ways, but there's one way that's, you can go on DigiKey or any other electronics store and just buy one of these circuits pre-made. First thing you can do, all right, this is 1000, this is 10 UF. So now take this one at 10 UF and shoot it out to like a 1 UF. So this one goes from 10, we're getting it up to like 18, but let's just pretend without the diode. Let's pretend that this goes from 10 to 20, and you could shoot it into 1 UF or 0.1 UF. Then you get up to 40 volts. The problem is it's just a tiny little cap. So, you're not going to have much capacitance. There's another way, and the scientist Vladimir Yutkin, he's Russian, he mentioned this one. So go 10 to 18, now you flip the cap over, and it's negative 18. Now you have 9.9, negative 18. Let's just make it simple again. 10, 20, flip it over, negative 20. Negative 20, 10, 30 volt difference. Now this will go to 60 volts. Flip it over again. It'll go to 120. And so you can do that, flipping it back and forth, and starting from a pretty small voltage, you can get up to, where you're running a spark gap. Now, what's the drawback there? Mention that you're discharging one cap into another, so there's no loss of charge. Doesn't apply when you flip this over So you go 10, now you have 20 volts, you flip it over, you're at negative 20. You're going to end up eventually at 40 volts when you do it a second time, but you have to eat that negative 20 volts. That's all lost charge. And it's just because it started off on the wrong side of the capacitor plate. So that charge gets lost. So the more times you do that, the less and less efficient the transformation becomes. But it is another way to transform voltage, making use of this, which is interesting. Now, a third thing you could do, and this is where you can go and buy these, is instead of this thing discharging into here, you short this cap, but you have the same conducting diode set up to go into the coil. And when you do that, you get a boost of voltage, and then when you short it again, you get another boost of voltage, and you can keep increasing the voltage here. And so let's set that up. So if we go here to Wikipedia, we can see a circuit diagram for the boost. And they also have the buck configuration and the buck boost. And just, real quick, they mention they're DC-DC converters. And they're also called switch mode power supplies. The buck and the buck boost are inverting, meaning that if you have a cap at 10 volts, when you shoot it out to a cap here, it's going to be at a negative voltage, whereas the boost is a non-inverting. So what we have now is we've got cap here, discharges through this yellow line to this switch. When that switch goes, it goes through this line of our coil out to this line of our coil, which is connected to the negative of the cap. So when this switch goes, it discharges the cap to 0 through the coil. And now we again have a conducting diode, and the conducting diode is coming off of this line out to the positive leg of our other cap, and the negatives are connected together. We see that everything is the same as we were doing before. The only difference now is I've put in a for loop, and right now we're just going to run through the for loop once, which doesn't make it much of a for loop, does it? But we'll just first look at what's going on with this cap, then what's going on with this cap, just one time, and everything's slowed down. And then we'll speed things up and let the thing run and show you why it's a boost converter. So here I'm just taking the code and I'm charging that cap up for 2 seconds, and then I'm discharging it for 2 seconds. Then we're just seeing that the cap charges and discharges. So we're at 10 volts and charges up, and then it shorts. So that's what we want. Charges up and then it shorts. Now when we do that, is anything going on in this cap? Which is, what we need to have happen. So when we move the meter over to this cap, we see that it's going up to 4.5 volts when this one's shorting. And there's your only connection there, is that conducting diode, and then this is the two negatives are connected. So it's doing what we want. Now, how do we make it transform voltage? Well, I was about to think this thing was kind of because I ran it 1,000 times, and it went from 10 to, maybe it was like 22 volts or something. Then I remember, well, we still have an LC tank circuit, so I set the timing for the discharge for the resonance of the caps and coil there, and before I knew it, I blew up a 100-volt switch. So you want to go slow and careful, and the thing does have some kick to it once you get it set right. So let's set it wrong first, and so what we're interested in is the discharge time, and so I'm just throwing 10 milliseconds there, and in addition to, that's the resonant frequency time. If we scroll up. I'm just doing this from memory, but it was right around 4,000. I think it might have been 4,200 from the last video, but it made a big difference at 4,000. So let's do it this way first, and we'll run it for 1,000 times, and then we'll see what shows up in the cap. Let's also turn the volts down to 5 so that hopefully I won't fry it again. Okay, so let's compile it, and well, we're starting at 8 volts. And away we go. 20. What are we at? 70. Shut it off. 96 volts there. Okay, so I darn near fried a second switch there, just going from 5 to 100 volts before I knew it. But fortunately, I was able to shut it down before that happened. So let's just do it for 100 times instead of 1,000. I think that would be better. And we see we're going from 5 to 37 volts. So that's the boost circuit. When you don't have the diode there and just let the switching do everything, that's what's called active or synchronous rectification. So I tried this like a year or two ago, and I think I was starting at like 10 or 20 volts, and I blew up the Arduino. I thought I blew up my laptop. The laptop just went blank. And then fortunately, like 5 minutes later, the laptop decided to come back from the dead. But I just fried the Arduino. So I think I'm gonna try that one off camera, like maybe 2 volts. And before I do it, I want to look at what's going on in this cap and this cap on the oscilloscope. And I bought a 2-channel oscilloscope, and so now I'll have a reason to use both channels, and so we can look at what's going on here and here, and try and have a clearer picture of why this thing transforms voltage like a scalded rabbit when you have it in resonance, and it hardly does anything at all if you just let the thing discharge all the way, or if you're out of resonance. So here what I'm doing is I'm pulsing the DC-DC converter, boost DC-DC converter, 3 times, and I'm letting the cap that we're discharging ring for a full 1/10 of a second, a little bit more than a 1/10 of a second. And I'm seeing what's showing up in that cap and in the other cap. So part of this I get, part of this is I don't really understand. But here, okay, so here is the yellow is this cap, and the purple is this cap. So we can see each time the voltage stepping up. And what I don't really get is, you would think that, so it looks like all of the voltage step up is from this first one, and the rest doesn't do anything. But you would still think it would have transformed voltage better than it did when it was out of resonance. But you see, that's where it's getting everything. Now the other thing, and I was wondering about this, which is cool to see, this one is where the cap starts off empty, and look at the shape of that. It's very damped, and then you get a little voltage in there, it's less damped, and then you get more voltage in there, it's less damped. I'm going to even go a little bit further, but you can see that the more loaded this is, the lower your Q factor, and that's what I would have expected. So that part makes sense to me. So here I've just done it 5 times, and you can really see. So there's where the cap was empty, and then there's the second one, third one, fourth one, fifth one. So that's the Q factor there. That's the Q factor when the cap was completely empty, and so that's kind of neat. So I think that's it, and I'll post this code I'll attach to the video description. I downloaded a program called Fritzing for diagramming circuits. I've never been big on that, but I'll give it a try because I keep using this same test bed, and I'll see if I can put together a diagram of this circuit, and then you too can have a boost DC-DC converter. In the next one, we'll do the buck boost DC-DC converter. And for people who've played around with the John Bedini simplified schoolgirl circuit, such as myself, you'll note when we build the buck boost DC-DC converter that it's the same thing. It's just in that iteration, the timing is being done by the spinning rotor instead of by an Arduino. But you again have an inverting DC-DC converter. But that's it. This is my edition of Fun with an Oscilloscope for today. So thanks for coming along, and take care, and ciao everyone.